Before we start this session, I just want to remind everyone that there is another very important session right after this one finishes, right here. So don't stand up after this one is done. You're in for another one. It's an ERI special lecture, geospatial structures, and enjoy both of these presentations. With that, again, just like yesterday, I have the most simple job in the universe, introducing someone who doesn't need an introduction. Jack Moehle is, in my opinion, he defines the highest standard of structural engineering research in general and research into the seismic performance of reinforced concrete structures in particular. I think his book is a seminal work on this subject. It's one of the few books that is always on my desk because I need it once every other day. He has been a professor at UC Berkeley, and he is one of a kind, a scholar and gentleman. With that, I ask Jack to come up.
Farzad, thanks so much for a really over-the-top introduction. And the lights are quite something else up here. I do want to thank the International Association for Earthquake Engineering and Computers and Structures for this opportunity. I thought I saw Ashraf somewhere in the audience. Take a bow, Ashraf. I'll do anything for applause. So, no, a good friend of mine and a generous individual. I was invited here, quite to my surprise, with a letter that requested a presentation, a little booklet, a meet and greet session. And the words, this is to document your efforts in the advancement of earthquake engineering. And I thought it was a little pretentious and self-serving, but I came anyway. Rather than just talking about my advances, I thought what I should do is talk about some of the experiences I've gone through. I've had opportunities, I've had people I've met, teams I've worked with. I've been in this business for almost 5 decades. And so I've met lots of people and had the opportunity to work on some of the most amazing projects since the earliest days of performance-based earthquake engineering. So 5 pieces, 1 per decade was my thought in starting this. Really the origin of the 5 pieces subtitle, in addition to the fact that Farzad called and said I need a title right away, was not the movie by Jack Nicholson, but a set of piano pieces by a true master, Igor Stravinsky, who had written 5 easy piano pieces for his children. And the idea was for them to be introductory, illustrative, and educational for his children. My intent here is to not get into the weeds, but to stay high up, introductory, illustrative, and educational for a broad audience. Luckily, we had an outstanding lecture by Steve Kramer yesterday that got into some of the details of the mathematics of performance-based earthquake engineering. And that makes an easy excuse for me to stay out of the mathematics and talk about kind of how it happened based on my experiences of what transpired. Let's see if I can. Give me a moment to catch up on things. First, I want to set the stage. George Hausner once wrote that earthquake engineering was really a 20th century and now a 20th and 21st century development. And we might think about that development starting perhaps in the beginning of the 20th century with the 1906 San Francisco earthquake, partially pictured on the left. It was an earthquake of many dimensions, with lessons to be learned in seismology, geology, geotechnical and structural engineering, emergency management, and societal aspects. I mean, it was everything earthquake because of its extent. I'd like to point out one individual, and this is Toshikazu Riki Sano, who was sent to San Francisco by the Imperial Earthquake Investigation Commission from Japan to investigate the effects on structures. And one of the interesting things that he came away with after studying overturned objects, gravestones and other things, was that it appeared, based on simple overturning static mechanics considerations, the peak ground acceleration was somewhere around 0.1 to 0.25 g. And later on, as he wrote his dissertation at the University of Tokyo, he came to the conclusion that for building design, a base shear of about 0.1 g was about right. Just a little over 2 years after that, the devastating Messina, Italy earthquake occurs in 1908. In that case, the Italian government set up a special commission to study the earthquake. I don't know the inner workings at all of the commission, but they came up with one recommendation that for one type of structure, the base shear should be about W over 12. All right, or 12%, 1/12 of the weight of the building. So this idea that a design base shear is about 1/10 of the weight of the building has been around for a long time, widely adopted for good reasons. You know, it's practical, it's empirical, it's consistent with observations. That's how we do earthquake engineering today. The idea of designing for forces was very familiar. The idea of having load combinations that you could combine with other load effects was easy. And the fact that it was inconsistent with the idea that earthquakes don't apply forces, they shake the base of a building, that inconsistency could be overlooked given the practicality of the overall method. And so it was largely for many, many years. Now, there were rapid advancements in the next quarter century. I point out a couple individuals from Caltech. A dapper-looking 26-year-old Professor Bio, and a little bit older George Hausner, who did seminal work on development of the response spectrum method. And given recordings from earthquakes that occurred in the 1930s and the 1940s that were measured in the United States, it became quite clear that the idea of a base acceleration times the weight of the structure wasn't really the truth about dynamic response, that there was in fact amplification that occurred in various period ranges. This, I think, set out a series of really decades of research and study, and quite frankly, a lot of arm waving about what exactly is going on in earthquake response. So we can design structures for 1/10 of their weight, and yet they perform under rather intense motions where there's amplified response because of the response amplification that we know from their early work. What's going on? And we can see some of the results of this, notions of overstrength, notions of nonlinear response. The idea of ductility comes into the language of earthquake-resistant design. And we see that everywhere in our research and our literature today, going back nearly 100 years now. Bringing this forward to where we are today, at a World Conference on Earthquake Engineering, we started the conferences on earthquake engineering in 1956. First World Conference was held at Berkeley, and there has been a conference every 4 years since then. And throughout that period, this notion that the base shear could be somewhere around 1/10 of the weight of a structure for success has persevered as perhaps one of the longest lasting, most persistent ideas in earthquake engineering, but less and less so as we learn more and more about the subject. Now, some interesting coincidences. 1956 was the year I was born. The first earthquake conference happened to be in Berkeley. I wasn't there then. But among the 5 easy pieces I want to talk about, the first one of them occurs in 1980, the year that I arrived at UC Berkeley, during the 7th World Conference on Earthquake Engineering. And the other 5 pieces are listed here with some brief titles so I can identify what were the activities that were going on related to those things. But in that 5-decade period, there's these 5 pieces that I want to talk about. So let's start on the first one. The first piece I want to talk about is displacement-based design. And the paper was presented by Mehta Sozin, 7th World Conference on Earthquake Engineering, 1980. You can see a picture of the first sheet of that paper. It was titled Review of Earthquake Response of Reinforced Concrete Buildings with a View to Displacement Control, or it was drift control, actually, that he wrote. Pictured on the right is a photograph of a test structure on a shaking table. Professor Sozin is the handsome fellow in the middle. The fellow just to his right is the scruffy person, it's me, as a graduate student. And we were standing on the shaking table for a publicity purpose to get a photograph to show what it was we were testing, what we were doing. That test model was being pulled toward the right by a cable up at the top. We were looking at the static response of the system under rather large forces. Eventually, one of these versions collapsed onto the table. They were different times. We were a little less concerned about risk on these tables. The shaking table there was 12 feet square, or a little over 3 meters square. It moved only in one horizontal direction. It was very limited, but it became the workhorse for Professor Sozin and the way he started thinking about displacement-based design. Sozin tested a series of progressively more complicated structures. Here's just a small sampling of what some of these structures look like. Some of them eventually became smaller in scale, so they would fit on this small table. Sozin wisely stayed away from problems associated with bond and anchorage failure and shear failure, because those kinds of things cannot be modeled in a small scale specimen like this. But flexure is relatively safe for modeling purposes. One of the things that Sozin wrote about in this paper was the fact that these structures cracked, yielded, they were clearly damaged, they responded to the nonlinear range of response, and yet they had characteristics very similar to response characteristics for linear structures. If we look at a set of waveforms on the left, those are displacement histories for a test structure. The waveforms are relatively smooth, like linear structures. The displaced shape is like a first mode shape. You don't see a lot of higher mode. Looking at acceleration responses, one can start to find similarities for multi-mode response, including the presence of nodal points and various other things. And Sozin also started noticing that there were characteristics of the drift amplitude that he could start calculating. And so he was continually focusing on this idea and trying to think where this could lead. As testing went along, this is actually a photograph from a little bit earlier, 1968, showing Sozin, the fellow standing. The fellow kneeling down on the shaking table is Shun Otani, who later had a magnificent career of his own at the University of Tokyo. And the fellow who's to the right of the shaking table, kneeling down and looking, is Polat Gulkan, who has had a long association with the IAEE and met you at Turkey. And one of the things that they got to looking at here was the load displacement hysteresis relationships of simple reinforced concrete structures on a shaking table, and noticing the characteristics of the shape of the structure, thinking in terms of the left figure about how the stiffness varied as a function of lateral drift, how that reduction in the equivalent stiffness might be used to estimate drift demand through nonlinear results. And on the right-hand side, some results from shaking table tests as well as sinusoidal motions, extracting what was the equivalent damping from the system as a function of what essentially the displacement ductility of the system was. Now, this was used initially as in the quest for an analysis tool that could be used to estimate the drifts of structures that were subjected to strong shaking. Eventually, they flipped the method around, though. They started thinking about this in a somewhat different way. And this different way came out in a paper in 1973 at a workshop that was held by the National Science Foundation. And in this paper, Sozin writes about a different approach to the earthquake-resistant design of reinforced concrete structures. And in this paper, he flips the idea. Rather than using the structure and the equivalent linearized properties to estimate demand, he says, hey, let's flip this. Let's think about first assuming that there's a tolerable displacement expressed as a multiple of the yield displacement, and you pick that displacement based on how much damage you think is acceptable. So you start with the idea that you want to control the damage, you pick the displacement, determine a reduced stiffness of the frame, step 2, in a period, find an equivalent or substitute damping based on what was shown in the previous slide that Gulkan had been working on, enter a linear response spectrum with the period and the damping, and get a base shear out of it. And he tried various schemes of this type. This eventually came out, being published as work that Professor Gulkan and Sozin had in papers in ACI Structural Journal. It entered into the thinking about a substitute structure design method. In effect, this is really the direct displacement design method. Not quite the same as it might be done today, but the idea of starting with the tolerable damage and working backwards to figure out what the structure should be was a huge insight, a very different way of thinking about this problem at the time. And I think it has to be attributed almost entirely to Sozin. Now, why was Sozin interested in displacement as opposed to forces? What we had before was, well, you get a base shear, 1/10, 1/12 of the weight of the structure, or something more complicated than that. Sozin's interest really came out of his experience in earthquake reconnaissance, looking at damage, and his experience in the laboratory looking at how damage develops in structures as they're moved. And watch this video if I can get it to run. There it goes. So this is a column subjected to axial force and cyclic lateral loading, effectively linear at this point, cracking, beginning to yield soon. There we go. We'll let this run a moment more. Much more extensive yielding. The force resistance of this structure, or this simple column, is determined by the longitudinal reinforcement. All right, the longitudinal reinforcement in the column establishes the moment strength. Provided the structure doesn't fail in shear or bond or anchorage, and provided it's pushed into the nonlinear range, the shear force that it's going to develop is determined by the moment capacity. And there it is. And it's not that shear force that fails the column. What fails the column is the deformation and the repetition of large displacement cycles that cause damage and that eventually lead to the failure. And Sozen's interest initially was primarily in the structure, I believe, and trying to establish how to control displacement, to control structural damage. He was also, though, interested later on in the non-structural parts. How do you control non-structural damage by controlling displacement? And it was a very different way of thinking about things at the time. Now, I don't want to get into detail on the subject, but drift and displacement have been a subject of our codes and our guidelines for many, many years. Sozen sometimes liked to point to this edition or earlier editions of the Structural Engineers Association of California's Blue Book. And there was an appendix there by a drift committee that had written its report in 1959. And the drift committee, if I can find my notes here, said that safety, of course, was important when considering drift. And so if you had elements that would get knocked out of place and fall on people and kill them, those had to be addressed. But beyond that, non-structural items and discomfort of occupants were not to be part of a building code because they demonstrated excessive paternalism. Paternalism, if you're not familiar, it's a complicated English word. More or less means excessive control by the government of things that the people really should be able to decide for themselves. And so Sozen, I think, got a kick out of that statement. He himself never, as far as I know, never nailed down or specified or recommended a particular drift that you should use, but maybe a range within which to work. So he was not into setting himself up, I think, to be criticized for what he selected. He also, though, was very interested in the idea of drift and detailing. And while he many, many times wrote about the idea that the amount of stirrups that you put in a beam or in a column is better related to displacement than to things like ductility, he avoided, in general, developing methods to calculate those kinds of things, to calculate displacement capacities. He relented, I think, only once that I know of, when we were developing the 1999 ACI building code. He was willing to adopt a procedure in which the amount of confining steel required in a shear wall was determined by how much the displacement was, provided the method was simple and provided there was only one significant digit in any of the coefficients that went into it. And this procedure still is there today. I want to close on this first piece, and I could spend all day on it, and I might if I don't stop now. But Sozen had a big team of students over many years, and I credit that team as shifting the focus from forces into displacements as a preferred means of identifying damage and design requirements. And the concept of relating performance and displacement and the notion of picking the displacement as a way of deciding if a design is good or not or what needs to be done with it, it today pervades methods of performance-based earthquake engineering. And while Mehta Sozen tended to disparage the notion of performance-based engineering every time I spoke with him, he really, I think, got the start of performance-based engineering, gets the credit in my book of getting us moving there. So that sets the stage that I wanted to start with. The second thing I wanted to say about performance-based earthquake engineering, the second of the 5 easy pieces, is one related to existing buildings and the assessment of those buildings. I wanted to point out first that in California, in the period of 1971 to 1994, there were many damaging earthquakes. There was a lot of shaking going on in California at that time. And those of you who are from California and young, get ready. It'll start up again sometime soon. Be prepared. But this was a very active period. We learned from those earthquakes that most modern buildings perform reasonably well. They did what they were expected to do. They were pretty safe. but many of them sustained damage that was not adequately controlled, mainly in non-structural systems. So that was a consideration that needed more attention. The existing building stock, on the other hand, was another story. And there was a lot of damage that occurred in existing buildings at the time. Owners began to be more aware of the problem of existing buildings. Many owners contacted engineers to look at buildings and start thinking about strengthening them. The word was strengthening at the time. And when they got into the business of negotiating fees on these things and the cost of construction, they started asking questions, well, exactly what am I getting for the money I'm going to put forward for this building? What kind of performance should I expect? And engineers were making up answers, in my opinion, doing their best job, but there was no standard to really judge this by. And performance-based earthquake engineering, I think, in California grew out of this many earthquakes and the need to answer the question, what kind of performance will I get if I retrofit a building and design for a higher performance level? Now, given the work that Sozin had been doing and others, there was awareness in the structural engineering community on the west coast of the US at that time that displacement mattered. You know, the original idea of seismic strengthening was that if the strength was less than about 3/4 of what the modern building code required, you added more strength to it to get it up to that minimum level. The thinking was beginning to change around the early 1990s into thinking about displacement-based ways of controlling damage. Now, if you start with a simple frame like the one illustrated in A, and you've got this red-orange column in the middle that's vulnerable, one way to fix the structure if it is inadequate is you can jacket the column or replace it or something of the sort. If you want to change the structural system to protect that column, the old thinking was you strengthen the building. The new thinking was that you had to control the displacements in the building. Now, this little set of cartoons came from some seminars that were used to train some practicing engineers on the new methods that were being developed on guidelines for seismic retrofitting, which came a couple years later. But this is, I think, a useful slide for illustrating the concept. We've got that vulnerable column. The lateral force resisting system is weak. It doesn't provide enough resistance to control displacements. In D, the column may be pushed beyond its shear capacity or beyond a capacity where it can continue to support vertical loads. The key to retrofitting in providing a supplementary system is to bring the drift back. And this seems routine today. But in 1991 or 2, this was not routine. This was not the usual way of thinking about retrofitting and repairing, rehabilitating buildings. FEMA, the Federal Emergency Management Agency, recognized the issues of existing buildings, and it started a program in the 1980s that really kicked off with the development of a document, FEMA 273, with a set of guidelines for the seismic retrofitting of existing buildings. Here are some of the key team members that were involved in the project. Many of them I think of as real masters of earthquake engineering who deserve to be invited soon to this stage. Ron Hamburger, in one of the presentations early on in the project, presented this slide during a presentation at an East Coast university. This slide became really the poster child, in a sense, for the project. And it shows a number of interesting things. One was the notion that there would be multiple performance objectives that one could choose. One could choose something related to a 25-year shaking level, and different performance level, versus a 2,500-year return period, for which you might consider being on the verge of collapse. So this idea of performance objectives with both demand and performance level both considered was kind of new. The response is definitely non-linear, which was fairly new at the time. And the idea of being very visual in the presentation of these different objectives so that you could explain to those property owners who wanted to know what they were getting when they asked the question, what am I getting for the amount of retrofitting you're proposing to give to me? It was very important to have all those things. I think for the first time, this committee went to work on trying to define what each of those limit states really was about. And so shown here is one of the tables, part of one of the tables from the FEMA 273 document. For concrete frames, if they're a primary part of the lateral force resisting system, in other words, they're supposed to resist the earthquake shaking primarily. For collapse prevention, life safety, et cetera, this is what that team decided was the right set of performance levels and how to describe them. Once the levels were described, the team had to go about the business of selecting ways of delivering a building that would do that. So there was discussion and there was provisions developed related to global modeling, how to do a global model. And for the first time in US practice at least, there was very explicit consideration not only of linear modeling, but non-linear modeling and analysis methods, both static and dynamic. For each component type, there had to be models developed, described. You had to understand what were the deformation limits and the criteria that were needed. And then for each one of those components, there was needed to be criteria that helped define whether they were force controlled, in other words, whether they were unable to yield without failure, or deformation controlled, whether they had the capacity to deform non-linearly without failing. And for those different kinds of components, criteria were needed for strength, for stiffness, and something totally new for the time was how to define the deformation capacity of a component that's yielding. Totally new thing. Not that we didn't know it was needed, but we didn't ever have criteria for that. Now, I want to just pause for a moment and also reflect on the fact that this had a huge impact on practice, on research, and on computer software development. Computer software development, we needed software that could do this kind of work. And the software companies stepped up and delivered that. We needed to understand criteria for deformation-controlled components, and we made a lot of them up at the time. But this provided a focus for research in the structural engineering community to do more tests where data were not available, and to create databases of test results from which to derive criteria for strength, for deformation capacity, and so forth. It opened the door because engineers had to use these procedures. The doors opened and new results came, software came, research, and practicing engineers started doing nonlinear analysis for the first time on a somewhat routine basis, and it changed the way practice developed from that point forward in California. These procedures were very widely used. The Berkeley campus is one example of sort of a retrofitting museum, so to speak. But we can find structures all over the United States that have been retrofitted by these procedures, and we think they've been very effective. One thing I didn't mention is that while we had performance objectives, they were really notional in the sense that we could state a life safety criterion, but we didn't actually calculate a risk of not achieving that criterion. And that was just too much to do at the time, and more time and more research was needed to take that next step. And that gets me to my third piece in the 5 easy pieces. So right about the end of the development of FEMA 273, it was apparent that we needed risk-based procedures. And we know that there's uncertainty in earthquake ground motion, in structural response, in the occurrence of damage, in the amount of time it takes to fix damage, and so forth. But it was a huge undertaking to figure out how to do that. We adopted Ron Hamburger's cartoon, updated the structure a little bit so we could call it our own in the Pacific Earthquake Engineering Research Center. Bill Holmes from Rutherford and Jacquin came to one of our research meetings and gave a presentation and told us we needed a performance engine that would be able to calculate not just serviceability states and life safety states and so forth, but would be able to tell us the cost for repair, the casualty rates, and the downtime. And we had no idea how to do it in the Earthquake Center, but we had really good people to work with. For example, Helmut Krawwinkler and Alan Cornell from Stanford University took on the task of trying to figure out how to formulate this notion of performance, how to actually do a calculation that put all the uncertainties together mathematically and enabled us to do a calculation of what was the risk of repair, of cost, et cetera. And the way the equation worked, just in the boxes, given a facility and a location, do a hazard analysis, do a structural analysis, damage analysis, loss analysis, and then come out with some variables about cost and time and activities required to restore it. Easy in the boxes, even easier if you just write down a triple integral. This triple integral essentially incorporates the ideas in the flow chart above. Many practicing engineers looked at this and said, "You've got to be kidding. No way are we going to do anything like that. You academics are nuts." Peter May, who was a social scientist, looked at the equation and he says, "You're oversimplifying the problem." And Peter was right. Solving the equation isn't easy, but we figured out ways to do it. One of the ways that it was solved, it was done in a little project with Tony Yang. I think Tony is here somewhere in the audience. We were working on trying to figure out a practical way to do the integrations and essentially set up a Monte Carlo scheme. And the idea was that given a facility, you did a hazard analysis, you selected some ground motions to represent the hazard, you input them into the structural model, calculated engineering demand parameters like drift and acceleration. You determined damage from that using a fragility relationship. How does damage of an infill, for example, relate to story drift? And you would then do this in a Monte Carlo study thousands of times so that you could characterize the distributions of the results. No way you could do it because just the nonlinear analysis at the time, and still today, takes too much computational time, and dealing with the results is just too difficult. So what we schemed was a technique where we did it a finite number of times, a smaller number of times, collected all the engineering demand parameters that were of interest. In this example, we did a 3-story building. We were interested in, we just did 11 ground motions at each of several hazard levels. And then we collected from that displacements, accelerations, and maybe base shears. And then we looked at that matrix and figured out what was the mean vector for each of those demand parameters, the standard deviation for each one of those, what was the correlation coefficient matrix like. So we could mathematically derive through an inverse process a series of demands that was statistically consistent with the results that we got from the nonlinear dynamic analysis. And so we could simulate mathematically the results that we were getting from nonlinear response history analyses. And here's a sampling. Here's 10 sample realizations of using a process like this. The nonlinear analysis could take an hour per run. This took a fraction of a second to do 100 of them. And so with something like this, we could develop realizations of what the earthquake demands were. And given those realizations, we would be able to do damage calculations, do loss calculations, et cetera, in a probabilistic way, taking all the uncertainties into account, and do it fast. And in this process, we could do things like calculate the probability of certain repair costs given an input motion. So here's some essentially fragility curves for cost. We could integrate those things and get what was an annual rate of exceeding a total repair cost, and take an area underneath that thing and get a mean cumulative annual total repair cost for a building. Or you could look in statistically at how individual components of the building were doing and find out which components of the building were being more heavily damaged than others, and try to find ways of of changing the structure, changing the clearances so that you could reduce those losses that were causing most of the cost. And it was a fascinating exercise. It was fun to develop and get it to actually work. This procedure was being developed by the Earthquake Center at the same time that FEMA was involved in another project, which was the FEMA P58 project, which was to develop the data necessary to determine what the losses were for a building of any general type with multiple building types that were being considered at the time. So there was a big team that worked on this, marvelous people to work with, developing definitions of what buildings were, what were the demand parameters you needed to work on. For each one of those components in a building, what kinds of damage could occur, at what drift levels did they occur, or acceleration levels if they were acceleration sensitive. What did they look like? What would it cost to repair them? How much time would it take to repair them? And when the information was all assembled with this performance calculation engine that we built at Bill Holmes's suggestion, you could put together almost anything on performance output. And David Marr, who I saw earlier yesterday, maybe in the audience, came up with this graphic for the FEMA P58 project. The idea on the vertical left axis of having different design bases would determine, as you move across, different casualty rates that you might expect. It might influence differently downtime that you might have, the probabilities of getting a red or a yellow or a green tag on your building, cost for repair, downtime costs. And as we were getting toward the end of the project, FEMA says you've got to include environmental costs as well. And once you've got the engine and you start inputting the data, creating fragility relations for all the things you need, this becomes kind of routine. So this was really the third, in my view, the third big piece in performance-based earthquake engineering was being able to quantify the risk of being in different damage levels. Now, once we had things like this, we started working on the problem of design of tall buildings. And there are many other types of buildings that could have been pursued, but there was a particular interest in California and throughout the West Coast at the time in pursuing taller buildings that were a little different from buildings that had been designed before. And they were outside the requirements of the code, the restrictions of the code. And so something different was needed. And here is a plot of the tallest building in any given year in California up until the year about 2015 or so. And as we start getting into around the year 2000, 2006, there was a bigger push coming along to design these buildings outside the prescription of the building code. And we had the tool to do it. We had this performance-based tool. The new building generation had different kinds of framing systems, odd geometries and cladding, There were combinations of structural systems within the building that just didn't match anything within the building code, and so we needed a performance-based approach. Lots of studies were done to try and figure out how to do this. Time doesn't permit going into many of them, but one of the little studies that was done was to do sample designs by practicing engineers of different structural systems and design them by different methods to see what the output was. This example is looking at a 42-story tall reinforced concrete dual system compared with a 42-story reinforced concrete core-only system. If you designed a core-only system in California at the time, you could only go up to about 15 stories or so. This is going way beyond that, and this then requires a design by a performance-based method. These were designed by two different design concepts, the code as it existed at the time, and then a concept we had, a notion of a design guideline that would allow us to carry out the design outside the code. And quick to the results. These two systems were designed two different ways. There's the initial cost in accordance with a real cost estimator. And below that was a calculation with this performance tool of what the losses were that we would calculate for each of these buildings. The base cost, if we were designing only by the code required system, we would have the dual system code design, $149 million US at the time. If we could shift to the performance-based design, we could go to a core wall and it would be a little bit less expensive. But it was something that we could design. It wasn't more expensive, and it had other attributes in terms of functionality that developers were interested in. In terms of average losses, compare the two. It's $323,000 calculated for the dual system by the code prescriptive design. Less losses for the core wall system. And a lot of this had to do with the losses because of the drift demands on flat plates, but also the shear demands that we would calculate on the core wall system. So with this in place, what was done was to start the process of writing a guideline that could be used by practicing engineers to implement this for the design of multiple buildings. Farzad, I'm very sorry, I had limited time tonight. I can only talk about the tall buildings guidelines and not the LA tall buildings guideline. But there's an equivalent, almost equivalent document in Southern California that gets used. It was decided pretty widely within the state that the best way to do the design was by picking a set of objectives for performance that were serviceability check for frequent earthquakes and a stability check for something that was a very rare shaking level. The design methods that were used involved specifying that you picked targeted yielding locations and locations that you protected from yielding. The structure was to be analyzed in certain ways with guidance provided on how to do the analysis and what had to be modeled. There were acceptance criteria developed, and the criteria are a little different in the two different documents I mentioned. But what was typically done is run a series of earthquake ground motions through a model of the building, check drift ratios, deformations in certain deformation-controlled elements like coupling beams, check strain limits against your modeling ability, and then for certain force-controlled elements, make sure that the forces stayed below what the force capacities were. And for those elements, there were load combinations that were developed that were intended to achieve the performance objectives stated in our building code. 10% or less probability of collapse in a maximum considered earthquake condition. And the building code, the materials code stepped up and developed resistance and strength reduction factors to fill in on the right side of these equations. These methods were used in many buildings up and down the west coast of the United States. I served on several of the peer review panels and started collecting data quietly on how each of these was performing, at least according to the calculations under nonlinear dynamic analysis. Story drift under service level earthquakes, pretty small for the most part. Under maximum considered earthquake, the maximum of the mean drifts never got above 3%. It's pretty high though, but 3%. Residual story drifts generally pretty low because they're core walls. Shears on the walls are the item that oftentimes control the design of these buildings. They get pushed up toward what we had established as a shear limit at the time. And then the rotation of the coupling beams oftentimes can be a controlling factor because the beams are constrained within the rotating walls. John Wallace, who's here, provided some test results from UCLA based on Panko Foundation testing to show what these things would look like given that level of shaking. And it was reasonable, at least within performance states that was considered non-collapse. We generally felt good. I certainly generally felt good about this process because we were providing a means to design buildings in a way that was considered effective, efficient, met performance objectives, and provide reasonable assurance for the occupants of these buildings that they could work and live and play in their urban centers. But one thing we really never checked for these buildings was whether their performance really met the societal expectations. And I think it's an area that we need to do some work, and it's in my last piece is what I want to chat about. This slide concept comes from something Professor Ken Elward presented as part of his 2022 EERI Distinguished Lecture. And Ken had been in Christchurch, New Zealand when this earthquake occurred and felt that the amount of loss, the damage, the downtime, the overall expenses associated with this earthquake were way beyond what societal expectations should be. And in his 2022 distinguished lecture proposed that there should be a consideration of repairability as part of the process. This idea that buildings should be repairable, that communities should be functional, I think is the next step and the ongoing step in performance-based earthquake engineering. And I want to spend just a few minutes on this. There is a project, another ATC project funded by FEMA, addressing this notion of functional recovery for our communities. And there is a flow chart that identifies multiple states. I'll, in the interest of time, just focus on building safety. But there's other aspects of functional recovery. As part of this focus on the building safety, one needs to be sure that a structure is at a point where it's safe to occupy. It doesn't have what we would call a safety critical damage state that would make the building suspect for being unable to perform again in an earthquake. There's a different project by FEMA-funded project that ATC is in the middle of with this cast of characters that has defined something referred to as safety critical damage. And safety critical damage by this document is damage corresponding to the point where strength degradation begins to occur. This point, DS2 up here. And this is based on multiple considerations and data. Shown here is some results in a paper by Opabola and others from 2023 that is looking at the lateral force displacement response of reinforced concrete components that are designed to be ductile without shear and bond and anchorage failures. And one of the things commonly observed is that look at the left figure, the point where strength degradation begins commonly corresponds to a point where reinforcement, longitudinal reinforcement buckling commences. It makes some sense. When a bar begins to buckle, the buckling results in very large strain in the longitudinal reinforcement. That results in low cycle fatigue damage that may fracture the bar. The buckling process results in a loss of confinement of the core. It results in softening of the core where that buckling is occurring. That causes localization of damage under further cycling. And once the localization happens, the strength decay is usually quick to follow. And we found this fairly consistently for columns, beams, and structural walls. And some of the data are shown there, not all. We've also looked at some results that, for example, the results from Kawashima and Kayama that, in this case, look at identical test columns that are subjected to different numbers of cycles. And as we get up to 4 delta Y, there's no strength loss. Whether there's 3 or 10 cycles up to then doesn't seem to matter. But once you get past the point where strength loss occurs, the amount of cycling matters and the strength decay accelerates. And the appearance of the damage is notably different. But prior to that point where safety critical damage occurs, things seem fairly stable. Not only does a structure need to have component response that's very stable, but the dynamics of the building has to be stable as well. And there have been studies, in the interest of time, I'll skip this one, work by Ashheim and Black that was very interesting. But other studies done by the ATC 145 team and some of the students working on that project were to collect data from shaking table experiments. And these data look at shaking table experiments of reinforced concrete ductile systems subjected to 2 earthquake runs, and sometimes even runs in between those 2 earthquake runs. And they include single-story to 10-story. They include moderate scale structures to full-scale structures on the E-defense system in Japan. And notably, the repeatability of the structure response, the ratio between the drift in a second run divided by the drift in a first run, is remarkably consistent, provided you don't push the building past a certain drift level and past the point where safety critical damage occurs. This idea is built into a draft methodology for doing inspection on a building. I'll avoid the details of that. But it's also been suggested by Opabola and Elwood, who may be here, that this idea could be used as a way to do design of a building. And the idea is you pick seismic hazard, do preliminary proportioning, do structural analysis, examine whether the safety critical damage is likely based on that result. If yes, reproportion things. If not, go to the structural detailing and document preparation. Now, this is a very simple flow chart. You have to understand, of course, that there's a lot of uncertainty in all the things we deal with in earthquake engineering, and so there's a lot of complexity built into the process under the covers here that I'm not showing. But they've run some examples. Here I pull out just 2 examples from a paper they recently published in Earthquake Spectra. Some 5-story reinforced concrete perimeter moment frames, a conventional design BR 3.0, and a damage control design BR 2.0. And one designed by the New Zealand code, the 3.0, the second with some upsizing of components to meet acceptance criteria for beam rotations such that it's less likely to have safety critical damage. And they've run through studies. On the left, the conventional design developing 26% under the 500-year return period of shaking, developing a probability of exceedance of that safety critical limit of 26%. The damage control design, where they're targeting a 20% exceedance level, they ended up with a 16% exceedance level. So they kind of exceeded what their target was. It's interesting that one can theoretically control the resulting damage, and the method seems to work fairly well. It's a little disconcerting that if you wanted to get even higher safety and reliability than just 16%, you'd have to go to quite a more stout or a completely different structural system to get it to work. They've also looked at some functional recovery results for the two different designs. In terms of functional recovery time under the 500-year return period shaking level, it's about 100 days for the conventional design that they looked at, 0 days for the other. It's one example of one building archetype with two different sizing options. More study of this type is needed to understand how to design an individual building and how to approach the recovery of entire regions. Closing thoughts, and then I'll finish. I presented this talk in sort of 5 high-level pieces of performance-based engineering. The first, I consider as kind of the father of performance-based earthquake engineering. It's the person who got us thinking about deformations and what damage is and how to focus on damage as a process. So Professor Sozin there. We talked about the idea that performance-based retrofit in the US was driven by societal needs at a time when we had many earthquakes, and how this really game-changing project developed nonlinear methods, focused the design method on displacement, came up with criteria, and again, was a game changer in the practice community. The next set of projects that developed a risk-based approach to this performance-based engineering created a performance tool that could be used to study various kinds of design methods, new materials, new configurations, new seismic environments. Very flexible tool that allowed us to make statements about the risk of damage and consequences. We, I think, have had an excellent experience in using these ideas to step outside the prescriptive provisions of our building codes and successfully design a series of buildings that are taller and more efficient than buildings we designed before. And it's important for us to use materials efficiently and to be flexible in our approach to design. We await the next earthquake as the demonstration that we're doing the right thing. And I think then the final step, piece number 5, which I encourage many of our young people in the audience to really pursue if you're not already on this one. It's for the next generation for sure. But looking at functional recovery, repair, design for repair, and those kinds of topics. With that, I thank you for your attention. We've got a marvelous set of tools at hand with performance-based earthquake engineering, and I think the promise ahead is really very bright. Thank you.